In this lesson, we'll address one of the most common questions about bioreactors. Does the type of wood chip matter? This relates to the learning objective about a bioreactor's mode of action. I'll also note that this video is really an intro to the wood chips where we answer some basic questions. And if you find yourself really geeking out on this, there is a second wood chip oriented video in the next module where we talk about wood chips from more of a design perspective. First of all, as I mentioned before, the carbon we want for heterotrophic denitrification in a bioreactor is an organic carbon that is available for microbes to access. So lots of different solid carbon media have been tried in this application. Shredded newspaper and cardboard, nutshells, ag residues like corn stove or corn cobs and different types of straw, different parts of trees, including leafy materials, and frankly, many of these work great, but they get consumed quickly or present design issues for flow like becoming gummy, like you can imagine the newspaper would. So all of that background just to say, wood chips are the most common fill media for bioreactors at this point in time due to a variety of reasons, including proven effectiveness, or in other words, dependability. Although this is still somewhat of a newer conservation practice, wood chip bioreactors have moved beyond the proof of concept. Wood chips not only tend to be widely available, which helps with the cost, but there is also a consistency in the product. We're not recommending some obscure, very specific unicorn that would be very difficult to find to fill a bioreactor with. This consistency in product has helped with the process of getting this engineered practice approved and recognized because you can develop standards for the process. And finally, and perhaps most importantly for why we use wood chips have a durability or a longevity that other carbon sources tend to not have. For example, the straw I showed on the last slide would get really burned up in a bioreactor within a couple months or maybe a year, whereas wood chips will last 5 to as many as 15 years. That's an important question I get a lot. How long do the wood chips last? So a quick preview of your answer is roughly about 10 years, but we'll go into detail on that in a later video where we talk about bioreactor recharge. So to the specific question, does the type of wood chip matter? I'll turn to a meta-analysis that was performed a couple years ago where softwood and hardwood wood chips were compared. Based on tree physiology, softwood is technically defined as a gymnosperm or conifer, and hardwood trees are angiosperms or trees with leaves. And we found that there was no statistically significant difference in the nitrate removal provided by either type of wood chip, hardwood versus softwood. One reason for that, I would hypothesize, is that nearly all fresh wood chips that I've come across have had a relatively static total carbon percentage in them. By that I mean that most wood chips have between 46 and 48% total carbon, regardless of the wood chip type. It's pretty consistent. And so I would say that the type of tree isn't strongly significant for bioreactor functioning. There is some guidance from the NRCS on this. Starting with, all wood chips will leach some tannins and other compounds that result in some color in the water, especially when the bioreactor is new. You can see the range of colored water in the picture from wood chips that have been soaked for different lengths of time. This leaching of color does reduce over time with flushing of the wood chips. For example, when we ran water through these 3 types of wood chips, you see the tannic acid concentrations in the water on the top and the true color in the water on the bottom. This true color metric is how color is measured in water that is colored but clear. That is colored but not turbid or cloudy. You see that the color of the water flushing out of the wood chips decreased over time, actually to the levels of that of streams in Illinois. This caution about high tannin woods in the NRCS guidance really has to do with oak wood, which is known to be especially high in tannin. And we did find this to be very true in our own work. Oak definitely does leach more tannin and much darker color compared to other wood chips initially, but it does reduce to the level of other wood chips with time and with enough flushing. The Illinois NRCS allows up to 50% blends of oak because it was difficult for wood chip suppliers and sawmills to guarantee that there was absolutely no oak in the chip material. Note, however, that other states may not allow this 50% exception. The other specific tree species guidance is to not use cedar or redwood. The redwood hasn't been an issue for us in Illinois because we don't have a lot of that type of tree. I don't think the cedar has really been a sticking point either, but I do want to point out that I have seen this study where cedar was used to fuel denitrification successfully. On one hand, our NRCS guidance is very useful for us to have because it sets some context, and on the other hand, I still think there's a lot to learn about the fill media that we use in bioreactors. Moving on, rather than the tree type or type of wood chip, I really look more for the physical properties of a given batch of wood chips. That starts with looking for a squarish, chip-shaped wood chip rather than shreds or mulch or hogged wood. That is, I like the chips in the beaker on the left rather than the beaker on the right. There are several design issues with using really shreddy types of woods. Firstly, those long shreds tend to bridge with each other, so the media on the right will compact differently than the chip-shaped wood chips on the left. Shredded media is less uniform than chipped media when we do particle size analyses with the different sieve sizes like you see there. We like individual wood chips in a given batch to be all very similar in size. So the wood chips that we like have a steeper curve on this particle size distribution graph, like the blue line, rather than the red line. Lastly, shredded woods tend to not only be less uniform than wood chips, but they also tend to have more fines. That is really apparent when you look at examples of hogged woods or hogged fuel, like I'm showing here. So again, what we want is a real chip shape so that water can flow through the wood chips like we want it to. In general, we want the wood chip particle sizes to be about 1/2 inch to 2 inches, but we recently realized that visually judging the size of wood chips is complicated because they're a 3D shape. So what you want to look for is the longest axis of the 3 axes, the longest axis of the wood chip, to be about 1 inch or more. The NRCS guidance for wood chips is to use chips with a 1 to 2 inch effective diameter. Note that term, effective diameter. I found that specific terminology a little confusing because when we manually measured a bunch of different wood chips, only the length dimension of those 3 dimensions that we measured fell within that guidance of 1 to 2 inches, and it consistently did so. Using the scientific method of a particle size distribution analysis with sieves, rather than just measurement by hand, the D50 from that analysis method is called the effective size, or median diameter, which tended to only be about 1/2 inch for all of the wood chips that we measured. That's definitely outside of that effective diameter criteria from the NRCS. So this might just be a terminology nuance, but nevertheless, that's how we developed our 1 inch criteria for the longest axis. I also recently realized, after looking at hundreds of pictures of wood chips, looking at pictures like what I'm showing on the screen is very different from standing in front of a bunch of piles of wood chips at a sawmill or a wood chip supplier and trying to assess if a wood chip meets a certain criteria. So I put some science to this by doing a power analysis and determined that if you measure the longest axis of 12 wood chips in a given batch, and those 12 wood chips measure more than 1 inch, you can be reasonably sure you're in the right size range. The last bullet is that you want to minimize leaves, including pine needles, bark, soil, and fines. Leaves, like in the picture, will degrade very quickly, which isn't the longevity that we want for a bioreactor. Those leaves also contain a lot of nitrogen in that green color. That's going to leach out, which defeats the purpose of a bioreactor. This last bullet that I'm discussing is consistent with the NRCS recommendations, and they go a little further to specify having a low percentage of fines in our wood chips. A lot of fines or dirt will restrict the flow, and it's all about getting water to flow through the wood chips. So what is a fine, and what percentage is acceptable? It seems like a fairly obvious thing, but it's still something we're working to quantify. For example, is a wood chip that has a size of 1/8 of an inch a fine, or 1/4 of an inch a fine? Is 5% acceptable? Is 10% of these fines acceptable? We just haven't quantified that yet. All of this said, we have done bioreactors using more shredded material like I'm showing. These pictures do not meet the NRCS wood chip specifications, in my opinion, but considering the number of bioreactors I'd like to have across our landscape, I think we need more research on exactly how flexible we can be with our wood chip specifications. I want to balance cost, practicality, performance, and longevity for bioreactors at scale. I hope all of this helps you the next time you're sourcing wood chips for a bioreactor. I'll see you next time.